I'm waiting. Thanks. So, good morning, everyone. Supposed to say good morning.
Good morning.
Sorry, I'm from Africa. Everybody does that in Africa. So, welcome to you all. Perimeter is a very, very special place. You're a very special group of people. Congratulations on getting here. We all feel very lucky to be here. We're all treated very well and sort of challenged to do the very best we can in what we do. So, but first thing I should emphasize is the main thing is to have fun. And if you're not having fun, I'm the guy you eventually get to see. So I'm the fun enforcer. All right. So that's a rule. You have to have fun. If you're not having fun, something's not right. So we're hopefully going to have fun together the next few weeks. I'm going to be teaching relativity. And again, if it's not fun, you need to tell me. And I'll try and change it around. I guess this is the beginning of a very long ordeal for you, 10 months of sort of sitting there with your mouths open under a fire hose. And the water will just be coming down at a huge rate. And one thing, so I will try to be gentle, but the one thing I should emphasize, you really don't need to know everything, okay? The most important thing is your enthusiasm, and don't kill it. Okay, so many different people make different contributions to physics in many, many different ways. And that's not always just by sort of following in the footsteps of everyone who's gone before, because there's so much stuff and so much very good stuff. It's almost impossible for anyone to master it. And so you need to find your own route. You need to find what excites you, what interests you, and follow your nose, develop your intuition, understand what you are good at and what you enjoy. Usually those are the same things. Okay, so enough of generalities. I'm going to teach you a little bit of relativity. And I'm always very happy to teach this course. I consider it to be the most conceptually beautiful aspect of physics, the most surprising, the strangest, maybe apart from quantum theory. But relativity has much more sort of intuitive, much more of an intuitive aspect to it to quantum theory. Quantum theory is really more mathematical. And so relativity really is a very aesthetically beautiful subject. And if I fail to make it so, then I apologize. But don't let that put you off. So we're going to begin with, in week 1, we're going to do special relativity and Maxwell's equations. This was the root of relativity. When Maxwell discovered the equations for electricity and magnetism, he didn't realize how far they would lead. But Maxwell's theory is really the foundation for our understanding of special relativity. It's the first example of a field theory, and it's still the most beautiful field theory. And it was the model for Einstein's field theory of gravity, general relativity, and for everything else, for the Dirac equation, the field theory of particles, and for the Higgs equation, and so on. So Maxwell really opened the door to everything. It's very appropriate we start with Maxwell. Do you know what's happening? Some very special event in, I think, 1 week's time. Scotland will vote on whether to be a country. And it's really interesting to follow. And Maxwell, of course, was a prime example of a Scottish intellectual who, if you read my book, which I'll advertise in a moment, I draw parallels between Scotland in the 18th century and Canada in the 21st century. And they're really quite interesting. But anyway, Maxwell was the root of 20th century physics. So we'll talk about that. We're also going to talk about particles, geodesics, and gravity. And then we're going to talk, I hope, about tensors and covariant derivatives. So this is the basic mathematics that we need for general relativity. We don't need much more. And I should also emphasize I will try to minimize the mathematics in this course. Sometimes students get upset. But essentially, to understand general relativity, you need linear algebra and calculus and nothing else. And I think it's very good to understand things in those basic terms before you move on to fancier mathematical discussions. So then in week 2, we're going to do curvature. So this means the curvature of space and time, which was Einstein's great insight, is that the curvature of space and time represents gravity. And then we'll do the Einstein field equations. Which were really modeled on Maxwell's equations for electricity and magnetism, electric and magnetic fields. And then we're going to do tests, experimental tests. And then of Einstein's theory of gravity. And then week 3, we're going to do black holes, which are one of the strangest predictions of Einstein's theory of general relativity, and very exciting today because we see black holes everywhere in the universe, and we're still trying to make sense of them, and then cosmology. So let me give you a little of my perspective on the field of theoretical physics, where it's going. This is a good introduction to leading edge topics in theoretical physics. Today couldn't be more exciting for physics. The last 3 years we've had absolutely spectacular experimental results, which are weird and surprising to everyone, okay? And the really weird thing about them is that the universe turned out to be simpler than theorists were expecting. So we had the discovery of the Higgs boson and nothing else. It's a lonely particle. All the theorists were predicting, or most theorists were predicting, tens of additional particles, supersymmetry and all kinds of other stuff would have to come along with Higgs. So far, it's not there. It may be there. Maybe they'll find it next year. But so far, something like 80 or 90% of the parameter space is ruled out of those theories. And the theorists are scratching their heads and wondering, how did nature get away with being so simple? Okay? And the second thing is last year's discovery by the Planck satellite of the structure of the universe on the very largest scales. And again, astoundingly simple. Okay, nothing but you can describe the entire pattern of what came out of the Big Bang with 2 numbers. An amplitude, the level of the fluctuations, and a slight deviation from perfect scale invariance being the same on all scales. And that's it, 2 numbers to describe what came out of the Big Bang. And yet all the theorists were talking about multiverses and string landscape and all kinds of chaotic theories, okay? Well, the universe spoke, and it is really simple. The universe is really simple on the tiniest scales we know, simple on the biggest scales we know. It's complicated in the middle, where we live, okay? And it just happens that the size of a living cell is the geometric mean between the Planck scale and the Hubble scale. The Hubble scale is defined by the vacuum energy in the universe today. It's a very fundamental scale. So something strange is going on. We don't understand it. We've got some ideas. I've got some ideas. They're not yet complete. But you could not be entering physics at a more interesting time. And what it requires is conceptual thinking. We need a conceptual break. We don't need more and more complicated models. We've had a lot of those, 30 years of models. And essentially, all these models have died. Okay? Or if they're not dead, they're irrelevant. They did not predict what we see. The Higgs model worked, okay, but that's 50 years old now. We need some new ideas, and we need deep ideas. And so I draw the parallel between today and the early 20th century, right, when Einstein and Planck and others realized, as brilliant as theoretical physics was, classical mechanics, electrodynamics, thermodynamics, these were incredibly impressive theories. As brilliant as they were, something was wrong. Something was deeply wrong. And it took Einstein to see through the mess and realize that something weird and wonderful was going on, both in relativity and with quantum mechanics. And I really feel like we're on the threshold of a similar change in physics. And so this is an absolutely wonderful time to do physics. So actually, the most important thing I should tell you about the Psi course is take every course with a big pinch of salt, okay? Because we don't know what we're doing, okay? And that's the fun, okay? That you might see something which we have all missed. Okay, so enough philosophy. I want to recommend a few books. There are an almost infinite number of books on relativity, but I'll just recommend a few. This one is quite a recent book by Tony Z. It's probably the most amusing of all of them. He's a very nice writer, and it's fun, and it's just fun to read. He does a wide range of topics. It has a completely misleading title. It's called Einstein Gravity in a Nutshell. Well, I never saw a nutshell as big as this. But, okay. What? It's a coconut shell. Okay, there we go. So that's a very nice book. Obviously, I can't cover all the topics that are covered in there. Then for a medium nut, here is Sean Carroll. This is, again, quite a popular book and fairly readable. And then for really gravity in a nutshell, as correctly described, I like this book. It's a little bit more mathematical, but without a lot of the, how should I say, unnecessary mathematical machinery of so these are two mathematicians, real experts in GR, and this book is nice because it's very concise. If you want to learn something, you can read it in 2 or 3 pages. One of the topics we cover, and personally, I find that very useful. I mean, I think physics essentially is for people who can't remember anything. Okay, and what you need to do is minimize the amount you remember and then be able to derive everything from that. Go ahead. Oh, this is Lane Houston. I'll write each of these down. Okay, so maybe Z and Carroll I don't need to write down. Anthony Z, Sean Carroll. And by the way, if you can't be bothered, if you don't want to buy Sean Carroll's book, it's online in an older version, the lecture notes, which are just as good as the book. And then Lane Houston. These are twistor theorists, actually. And K.P. Todd. I believe there are lots of copies of this in the library. Introduction to General Relativity. And another book, which there are lots of other books, but one of them I especially recommend you look at sometime is Dirac's book on general relativity. It's a tiny book. It's like 80 pages and just contains everything in an extremely concise and beautiful form. Some other books which are useful. Steven Weinberg's book on general relativity is a masterpiece. It irritated all of the general relativists because he uses coordinates for everything. And he actually, the nice thing about this book, he proves everything. Okay, everything he does, he proves. Okay, sometimes the notation is long and cumbersome, but it's all there, and a fantastic book. And then some little books. So let me just mention those ones as well. Dirac, Weinberg. And then you cannot do any better than at some point looking at Einstein's original papers. Einstein. So he wrote a lovely popular book called The Theory of Relativity. And then there's a very nice collection of papers. Called The Principle of Relativity. Which is a Dover book. So if you're in a second-hand bookstore, look out for that one. For example, it contains Einstein's paper showing that E equals mc squared, which is 3 pages long and has no references. Okay. Actually, Peter Higgs went one better than Einstein. Peter Higgs' paper is 1.5 pages, saying that there must be a Higgs boson. So length is no guarantee of excellence. Okay, so those are books. Let me see if I can control this thing. Right. So I'm going to begin over here because I want to leave these equations up. So let's start with Maxwell. And he was working in the 1850s and 1860s. And what Maxwell tried to do was to make sense of electricity and magnetism. These had been discovered experimentally, and there were various laws known, mathematical laws. They weren't really formulated very precisely, but that's part of what Maxwell began by doing, was to translate these empirical or semi-empirical laws into calculus. And actually, in many ways, Maxwell invented partial differential equations. He had to invent them in order to write down these equations. Nevertheless, they're known as Gauss's law. Okay, so this law tells us the electric field in terms of the charge density. That means the charge per unit volume of the electric charge per unit volume. And this number, epsilon naught, I'm going to write them down in SI units. So epsilon naught is equal to 1 over 4 pi times 1 over 9 times 10 to the 9. And then there was a second law, as well as electric. So this law basically tells you how electric fields spread out from electric charges. It implies Coulomb's law, for example. From this law, you can deduce everything there is in electrostatics. Similarly, people discovered magnetic fields. There were magnetic monopoles, and they were not magnetic monopoles. There were magnets. Magnets have a north and a south pole. There were no monopoles discovered, but magnets are dipoles. And the fact there are no monopoles meant that the right-hand side of this equation is 0. There's no such thing as magnetic charge in nature. But nevertheless, the magnetic field obeyed a similar law, that it spreads out away from sources of magnetic field. The magnetic field spreads out according to this law, which as far as I know doesn't have a particular name. The magnetic field is divergence-free. I should write down the notation. This gradient is d by dx, d by dy, d by dz. And I'm going to write spatial vectors by writing the letter with an underline. So E is Ex, Ey, Ez. And of course, div E is equal to Dex dx plus Dey dy plus Dez dz, etc. Then there was Faraday's law. And Faraday linked magnetic to electric fields by showing that if you have a changing magnetic field, so a changing magnetic field, it acts as a source for an electric field in a very peculiar way, that the change in the magnetic field causes a curl in the electric field, curl or circulation in the electric field. And of course, curl E is a vector whose ith component is epsilon ijk d by dx j ek, right, where I, j, k are 1, 2, 3. So this law was discovered experimentally by Faraday. Faraday didn't know mathematics, and so Faraday could only describe qualitatively what happened. One of Maxwell's first achievements, actually, was to try to put Faraday's law into mathematical form, and he wrote to Faraday. And Faraday wrote this, explained afterwards that he was almost terrified when he saw Maxwell's paper. Maxwell, I think, was 24 at the time. And he wrote to Faraday, he said, I think your law really should look like this. And Faraday was terrified by this mathematical power, and realized there was something very deep there. And then Faraday, and Maxwell in turn always accredited his discoveries to Faraday. Maxwell never took credit himself for the laws of electromagnetism. He said it's all due to Faraday. Faraday really discovered this. All I did was to translate it into equations. Okay, it's good for theorists to be humble. I wish they were a bit more humble today. Okay. And finally, there was Ampere's law, again, really translated into mathematics by Maxwell, which said that, so this is current density. J is a current density. What that means is if you want to know, if you have some surface, S, and you want to know how much electric current is going through a surface, then the current is equal to J dot ds. Okay, so J is a current per unit, electric current per unit area. And I, of course, is the rate of change of the charge. So the current flows through the area, and if you count how much charge flows through per unit time, it's given by integral J dot ds. This quantity mu naught is 4 pi times 10 to the minus 7. Actually, this is a definition. That one is an experimentally measured value. And so Maxwell formalized these laws of electricity and magnetism, that electric charges cause electric fields, electric currents cause magnetic fields, changing magnetic fields cause electric fields. He wrote these equations down. And then suddenly he notices a big problem, okay, which is they're inconsistent. Can anyone tell me how they're inconsistent? Why are these inconsistent?
Because they imply that the continuity equation doesn't hold. Yeah.
Yes. Okay, so the continuity equation for electric charge conservation, also called the continuity equation, reads d rho dt equals minus div j. Okay, and that's simply the statement that if I take any volume V and I work out the charge in it, total charge is d3x rho over the volume V, then the change dq dt, if I differentiate this, I can bring the time derivative under the integral. Rho is a function of x and t, so I just differentiate the rho. I can use this equation to write this as minus integral j dot ds, okay, where S is the surface of this volume V. So that's just saying that the rate of change of the charge is the rate at which the charge leaves the region. So since that holds for any volume V, you can take it for an infinitesimally small volume, and then you see that this equation must be true. So you have that equation. Now, if you look at these two equations, well, let's begin with the ones that don't involve charges or currents, these two, okay? So you can see these two are compatible, because if I take the divergence of this one, div B is 0, right, on the right-hand side. Sorry, if I take a divergence of this one and use that equation, the right-hand side is 0 because partial derivatives commute, and div B is 0, so this divergence of this is 0. Left-hand side, div of a curl is 0, okay? And because div of a curl is anti-symmetric. Right, so you have di epsilon ijk dj ek. These derivatives commute, so di dj is dj di, but this guy's anti-symmetric, and so this is automatically 0. So these two are consistent. Okay, but what about these two? Well, you see, if I take divergence of this side, I get 0, because div curl is 0. But div j is not necessarily 0. Why is div j 0? Div j represents the change in the charge density. So this one is not, this equation is not identically satisfied. It's only satisfied if charges are not flowing. Right? Because if charges are not flowing, rho is constant in time, div j is 0, then this one is consistent. In general, it's not consistent. So according to this equation, another way of saying it, according to this one, I could never change the charge density anywhere. Okay, I can't move around an electric charge according to this equation. That's wrong. So what Maxwell noticed is that if he changes this equation, right, by adding a term, mu naught epsilon naught dE dt, then it's consistent again, because I take the divergence of this side, I get 0. Take the divergence of this side, I get div j. By this equation, it's minus mu naught d rho dt. Go up to here, minus mu naught d rho dt is epsilon naught div e, and d by dt of div e. And this term is designed exactly to cancel that term. Okay, so this was Maxwell's addition to Ampere's law. And with that addition, these equations are now consistent. Okay, so Maxwell added a term to make the equations consistent. How big is this term? Okay, you would worry if it completely spoiled the equations. But if you multiply mu naught with epsilon naught, you see mu naught epsilon naught is equal to 1 over 9 times 10 to the 18. It's a small number. Okay, and in fact, that's a very special number. That will turn out to be 1 over the speed of light squared. And so the term Maxwell added was small because the speed of light is so huge. Now, having added this term and made the equations consistent, Maxwell asked himself the following question. Well, I have a set of equations here. What happens if I don't have any charge or density? But now he noticed there are interesting solutions even when rho and j equals 0. Okay, yeah.
Maybe just an important thing, but when you wrote not epsilon naught, I think the order of the 10 is not.
Oh, sorry, 16. Thank you. Thank you. It is important. Okay, so Maxwell noticed there are interesting solutions. So stare at those equations, and when rho and j are 0, and so, for example, let's take the fourth equation, okay, and calculate d2e dt squared. So this will be 1 over mu naught epsilon naught. From here, curl of dB dt, but dB dt is minus curl e. So this will be minus curl of curl e. Okay? So if we now calculate that, we need to calculate the curl twice, so epsilon ijk dj. That's one curl, epsilon klm dl em. Okay, and then we're going to use this identity that epsilon ijk epsilon klm is delta il delta km minus delta im delta kl. Is everybody familiar with that? Okay. And so we can see that this is equal to so I've got delta il, so this becomes a di, delta jm, this becomes a div e. And then I have a delta im, so I have a, with a minus sign, ei, and then I have a delta im delta jl, so this becomes a grad squared. Okay, but div e is 0 because there's no charge density. And so I'm just left with grad squared. So over here, I get 1 over mu naught epsilon naught del squared of E. Okay, so that equation is the wave equation. And it describes waves which propagate with a speed given by this number. For waves with speed c mu naught epsilon naught. You can see this quantity is the square of a speed by dimensions, just because here I have 1 over length squared, here I have 1 over time squared. So 1 over mu naught epsilon naught has dimensions of length squared over time squared. And so a square root of it will give you a speed. And so then Maxwell plugged in the numbers, and 1 over square root mu naught epsilon naught square rooted is this number, and Maxwell noticed that was the number he got was within a few percent of the speed of light, which had been measured. So I consider this to be the greatest discovery ever in all of science. Okay, to start from some messy equations to fiddle around with them. They described electric fields, magnetic fields. You do some mathematical calculation, and what? You explain light. You know, it's completely insane. And so obviously Maxwell was pretty thrilled by this. But with the explanation, of course, he didn't just explain light. He explained all of radio waves and X-rays and gamma rays, and predicted all kinds of phenomena, which in time led to all the technologies which surround us. Right? Where would we be without our smartphones and our wireless and TV transmissions or whatever? Maybe we'd be a lot happier. But this discovery opened the way to all of that stuff. And nothing ever works. That's interesting. So Maxwell discovered explained the nature of light based on these equations. And so the wave solutions, which we'll use later, e.g. a plane wave in polarized in the z direction. So that means we have our coordinates x, y, z. We have a wave which travels along in the x direction. And the solution looks like this. The electric field is 0 it's moving in the x direction. The electric field is transverse. It's not in the x direction. That's essentially because div E is 0. And it looks like some arbitrary function of x minus ct. Okay, any function of x minus ct will satisfy the wave equation. So this is an arbitrary function. And the magnetic field, if you use this equation, this relates the time derivative of the magnetic field to the curl of the electric field. So the curl of this electric field involves d by dx of Ez. So the curl is in the y direction. And that gives you the magnetic field. And when you work it out, you'll find that the magnetic field is minus Ez over c times x minus ct, 0. So the electric field is this way, and the magnetic field is transverse. It's pointing in the y direction, b. And the two happily propagate together. Oh, sorry, I went backwards. Okay. So this was the greatest discovery of all time. People obviously were very interested in it and its experimental implications. Eventually, it led to the discovery of radio, transmission of radio, detection of the first transatlantic radio signal. Do you know where that happened? Where did that happen? The Marconi detected. Pardon?
It was sent from Cape Cod, I think.
No.
No?
It wasn't Canada. No, he went to St. John's in Newfoundland, which is the eastern point of Canada.
There's a Marconi Beach in Cape Cod. Maybe he sent like the second one.
US always claims credit. It's done by an Italian in Canada. Okay. Anyway, you can see I've been here too long. I'm becoming a nationalist. So anyway, so this led to great discoveries and experiments, but you see, these equations were still pretty messy. In fact, when Maxwell wrote them out, they took pages and pages and pages because he didn't even use this notation. This notation was invented by Heaviside, who was an engineer in 1890, something like that. But in fact, even this didn't get to the heart of the Maxwell equations. It took people, and it took until 1904, so roughly 50 years, because Maxwell began to understand these in 1854. It took about 50 years for people to realize what these equations really, or how to simplify these equations one step further. Okay, and the key insight is that this is really strange. You're predicting a speed. You've got some laws of physics that predict a speed. Well, a speed relative to what? Normally, speeds are relative, right? If something's moving along and I run after it, the speed changes. Depends on how fast I'm moving. Here, the speed comes out, and there's no mention of anybody else. It's just the speed. How can the laws of physics predict a speed? And there's an immediate contradiction with principles which go back to Galileo. Galileo pointed out that there should not be any absolute speeds. Okay? Galileo said that he has this beautiful passage where he imagines sitting in the hold of a ship, okay? And the ship is sailing along, and there's a fly buzzing around, okay? And according to Galileo, the fly will buzz around him in the hold of a ship just as it would if he was at rest on land and saw the fly buzzing around, okay? The motion he observes of the fly is not influenced by the fact that the ship is moving. That was the Galilean principle of relativity. And as soon as you predict a speed, you violate that principle, okay? So amazingly, it took people, maybe not amazingly, it took people 50 years to realize there was this deep, deep contradiction between Maxwell's discovery and Newtonian mechanics based on Galileo. Okay, so these two things are just in conflict. And the way it was resolved was by understanding these equations better. Okay, and so let me now rewrite those equations. So in fact, the Maxwell equations have an amazing symmetry. First realized by Hendrik Lorentz in 1904, and that was the basis for Einstein's discovery of relativity in 1905, have an amazing symmetry connecting space and time. So to make the symmetry obvious, we're going to rewrite these equations in a better notation. And we're going to begin. So a lot of this will seem a little bit arbitrary. Why am I doing this? I can only really justify it after the fact. Okay, so just bear with me. I'm just telling you the symmetry connects space and time, and then without justification, I'm going to introduce this notation. That I'm going to write down the coordinates in space and time, the spatial coordinates. So in my course, Latin indices go 1, 2, 3. Okay, x, y, z. So x1 is x, x2 is y, x3 is z. And Greek indices go from alpha is 0, 1, 2, 3. And so the way to simplify the Maxwell equations, you see you have partial derivatives with respect to x, respect to t. They're both first order. So what you try to do is combine the two of them. And so the first thing we want to write down is d by dx alpha, which is d sub alpha. And that's going to be 1 over c d by dt and del. Can anyone tell me why I put the c in here? Just dimensions. Okay. The first rule of tensors and of understanding relativity is if you make one object, every component of it better have the same dimensions. Okay. So the only way to make time into space dimensionally is to multiply it by c. Okay, so every time I write down a tensor, each component, these are examples of tensors, the simplest examples. Every component has the same dimensions. It has to have that. And now we introduce a funny symbol. This is hard to justify initially, but we're going to introduce a matrix called eta. And the role of this matrix is to distinguish space and time. Okay, space is not exactly the same as time. It's almost exactly, but there's a minus sign, which distinguishes between space and time. And so this is a 4 by 4 matrix, which is 0 everywhere except on the diagonal, and the diagonal elements are just 1, except for the 0, 0 component. So this is 0, 1, 2, 3. 0, 0 component is minus 1. Okay, so that looks a bit arbitrary. We just invented this matrix. It turns out it's absolutely fundamental. And this eta will turn into the metric of space-time. And in fact, generalizing eta will be the way we'll get gravity. We'll see that later this week. So we're going to introduce this matrix. Why do I introduce it? In the first description, let me notice that eta alpha beta times d alpha d beta. Now, when I write this down, just as in vector calculus, when I have repeated indices, I have to sum them. So eta alpha beta d alpha d beta means you consider the sum of all values of alpha, all values of beta. And because this is diagonal, I get minus 1 over c squared d2 dt squared plus del squared. And this is the wave operator. Okay, so if you're unifying space and time, you know you have some equations which are going to give wave solutions. It makes perfect sense to introduce this guy eta, because now I have a compact notation for my wave operator. We're also going to introduce the inverse, and this is just the matrix inverse of eta alpha beta, and this is eta with downstairs indices. Minus 1, 1, 1, 1, again, zeros everywhere else. So it's the same matrix. And the property of the inverse, of course, is that eta alpha beta delta is delta alpha delta. Okay, it's just the matrix index inverse. So you'll notice we have some quantities with downstairs indices, some quantities with upstairs indices. This eta quantity is what we'll use to raise and lower indices. So we're going to define d alpha to be with an upper index to be eta alpha beta d beta, etc. Okay, so as I said, you just have to sort of accept this on faith for the moment, that this is a notation which ultimately will prove its value. And now we're going to start doing the really clever stuff, which is to say, I want to combine E and B into one object. Okay? I combined space and time into one object here, space-time coordinate. How do I combine electric and magnetic fields into one object? There are 3 components of electric field, 3 components of magnetic field, which are independent. How do I write down something in this notation which has 6 components? What is it? It's not a 4-vector. These things are called 4 vectors because they have 4 components. An antisymmetric tensor, exactly. Okay? So to combine E with B, well, let's say we combine E and B into one object. Okay, it can't be a vector because that has 4 indices. But it can be this antisymmetric tensor, F alpha beta, which is minus F beta alpha. Okay, why? Because an antisymmetric matrix must be 0 on the diagonal, but then it has 6 non-zero components off the diagonal, and of course the lower ones are just minus the upper ones. Okay, so antisymmetric tensor has 6 independent components. And that's just what you need to unify the electric and the magnetic field. So let's write that down, F alpha beta. So it's antisymmetric, so it has to be 0 on the diagonal. And then let's put all the electric components into the 0I components, the components linking space and time. So this turns out to be EX over C, EY over C, EZ over C. And then anti-symmetry makes this minus EX over C, minus EY over C, minus EZ over C. And then the magnetic field we'll put in the other components, and we do it like this. BZ minus BY, BX, and then by anti-symmetry minus BZ, BY minus BX, i.e. F 0I is equal to minus EI over C. And because 0I, this 0 is the row, I is the column. So 0I means that, that row. F0I is minus EI over C, and Fij is equal to epsilon ijk bk. And that gives you all of these formulae. Because we had a vector, we've got to transform it into a matrix. We use this epsilon symbol. Okay, so we've invented this quantity F, which is called the field strength tensor. And likewise, now we're going to have to use this eta guy to raise indices. We define f alpha beta with raised indices to be eta f gamma delta. So f we define with lowered indices, but we can raise the two indices using eta. All this does is stick in a bunch of minus signs, okay? And as a matrix, if you work it out, obviously the 0I components are going to get one minus sign because one of these will be eta 0, 0, which is minus 1. The ij components, this guy is just a delta in the I and j direction. So the ij components won't change sign. So all that happens is that the electric field parts change sign and the magnetic field parts do not. And then the other components are just as before. Bz minus by, bx minus bx, by minus bz. Okay, finally, we need to do something about rho and j. We'll define, how am I going to unify rho and j? Rho is one quantity, j is three quantities. How do I unify them? Four vector, yeah? So we'll define the four vector current, j alpha, and we've got to get the dimensions the same, so it's rho c. These are the dimensions of a current. Current is electric charge per unit area per unit time. And so this guy is going to have current in the spatial indices. You've got to multiply the rho is a charge per volume. Okay, so you better multiply it by a length and divide it by a time, i.e. a speed, in order to get something with the right dimensions. So that's the four vector current. And then Maxwell's equations are d alpha f alpha beta equals minus mu naught j beta. And that equation gives you the first and the last of Maxwell's equations, the ones with charge and current in them. And the second and third equations, you see, don't involve charges at all. And those equations look like this. D alpha f beta gamma plus d gamma f alpha beta plus d beta f gamma alpha equals 0. This equation, there are three terms, but really it's the same term. All you're doing is cycling the indices. Okay, so here they're alpha, beta, gamma. I just move the gamma to the front and shunt the alpha and beta down. And then I move the beta around to the front and shunt the gamma and alpha down. So the claim is that these two equations describe all four Maxwell equations. So we'll check that in a moment. But I think you can already see it's a simplification. Okay, there's no, we've put together electric and magnetic fields into one object, charges and currents into another object, and so from four equations we've gone to two. Okay. Some things become quite obvious with these equations. For example, that there are wave solutions with the speed of light. Okay? If j beta is 0, there's no electric charges and currents, let us differentiate this guy. So let's call this one 1 and 2. And let's calculate d alpha of 2, of equation 2. Right? So what is this? This is d alpha f beta gamma plus d gamma. Now remember, partial derivatives commute, so I can move the d alpha past. D alpha f alpha beta plus d beta d alpha f gamma alpha equals 0. Okay? But the first equation implies that this guy is 0. Right? You see, if d alpha f alpha beta equals 0, this implies that d alpha of f alpha beta equals 0. And I can just lower this index with an eta. Eta is a constant, so constant matrix. So it implies this. So any raising or lowering of the indices doesn't change the fact that it's 0. So it's 0 in one form, it's 0 in all forms. Okay, so this is 0 by 1. And this guy similarly. You see, f is antisymmetric. So this equals to minus f alpha gamma. And so this term here is proportional to d alpha f alpha gamma. It's also 0. Equals 0 by 1. And so what does this imply? That d alpha of f beta gamma equals 0. And this implies wave solutions. Okay, that the field strength tensor obeys the wave equation if there are no charges and currents. So to some extent, we've simplified the calculations, okay, by going to this notation. Let's check that that's true. I'll only check one of them, and I'll leave the rest to you. So let's check. Let us write down equation 2 for alpha beta gamma equals ijk, spatial components. Okay, so what it tells you is that Fij, comma k, and I'll use this notation of commas, d by dxj of some quantity, I'll denote as a comma j, just to make it smaller. So Fij, comma k, this is d by dxk, k of Fij. So Fijk plus, and then I cycle things round. So Fki, comma j plus Fjk, comma I equals 0. So those are the spatial components of equation 2. And so now this is an object with 3 indices, so it's crying out to be multiplied with epsilon, Fij, comma k. But this, of course, is epsilon ijk, epsilon ijl, because Fij is epsilon ijl from up there times b. BL, comma k. And when we look at this quantity, you see it's 2 epsilons, but with 2 of the indices summed over. Okay, so I've got to take my formula, delta I, so let's, I take this formula, epsilon ijk, epsilon, let's not sum them initially, IML equals delta JM delta KL minus delta JL delta KM. Okay, and now I'm going to set M equals J. So this M is J, and M is J. And then I use the fact that, what's delta JJ when I sum over J? This quantity. That means delta 1, 1 plus delta 2, 2 plus delta 3, 3, right? Because I've got to sum. So this is equal to 3 delta KL. And this guy is delta JL delta KJ. It means this is only non-zero if J equals K. So this is minus delta KL. And so this is twice delta KL. Okay, so when you sum over a pair of indices, you get 2 delta KL. So this gives me 2. And then delta KL means this is the divergence of B. And so what we get is that, so if I multiply this equation with epsilon ijk, the first term just gives me 2 div B. What about the second terms? Well, the second terms, you can check that epsilon ijk fki comma j so let's look at these indices. If I put, so here you see I've contracted the first 2 with the indices of the f, and the last with the derivative. So if I move this around, I want this is minus epsilon ik comma epsilon ikj, because I interchanged 2 indices, okay, times f ki comma j, and now these are in the wrong order, but f is antisymmetric, so this is equal to plus epsilon ikj fik comma j. So what you realize is that epsilon contracted with this term is precisely the same as epsilon contracted with that term. Okay, so all 3 terms give the same. And so what we deduce is that div B equals 0. I should say here, contract with epsilon ijk. And this is the first term. Let's do another one, so we've managed to get Maxwell's second equation out of this. I'll do one more, and then I'll leave the rest to you. So let's look at, we'll look at equation 2 again, but alpha, beta, gamma is going to be 0, j, k. So we've got f 0, j, comma, k plus f k 0, comma, j plus f j, k, comma, 0 equals 0. Now, if you remember, F0J, that's the first row of the F matrix. So this guy is just where is the F matrix? Is it gone? Yeah, it's gone. So that's the F with upstairs indices. We want the F with downstairs indices. All that happened is that the first row had minus signs. So here I've got minus EJ comma K over C. This term here, FK0, so now the column is 0, and so I've got plus E K comma J over C. And then here I've got epsilon I JKL BL dot, well, let's write it as time derivative, d by dt BL 1 over, I don't think there's a 1 over C there. No. Yes, there is, because of the derivative. Remember, d by dx0 is 1 over C d by dt. And so now, obviously, what we want to do is to contract this with epsilon, so times epsilon ijk. And what we're going to do here is obviously get minus curl E. Sorry, it's not. It's plus curl E, because this is d by dx j e k. So if I multiply epsilon I j k, I get twice curl E I over C. And then here I get plus 2. Remember, epsilon contracted with itself with 2 indices summed just gives 2 delta IL. So here I get 2 dBl dt over C. And so this implies that dB dt, oh, how did we write it? This implies that curl E equals minus dB dt, which was, sorry? Oh, thank you. Okay, so now we've managed to get out of the second sort of new Maxwell equation. We've got these 2 equations, and I'll leave the rest of it to you to check that the other 2 equations emerge from the inhomogeneous Maxwell equation, the one with the source. So let's do one more thing to show the value of this. That, as you know, often when we do electrodynamics, it's useful to introduce a potential function, an electric potential and a magnetic vector potential. And we combine these 2 things into a 4-vector potential, which we call A mu. And this is going to be the electric potential over C. And again, if you think about units, you will discover that electric potential is defined so that the electric field is minus the gradient of the electric potential. Magnetic potential is initially in magnetostatics defined so B is curl A. And this 4-vector potential is defined this way. Again, both components have the same dimensions. Obviously, if I lower the index, then I reverse the sign of the time component, and I leave the space component the same. Space component's the same. And now we notice that, in fact, the relationship of A mu to F mu nu is very simple. It's d mu A nu minus d nu A mu. And so, for example, Fij, which is epsilon ijk bk, is dij minus dj ai. If I contract the two indices on the epsilon here with another epsilon, I'm going to get 2 times delta on the left-hand side. And so what I'm going to get, so multiply this by epsilon ijl, I'm going to get 2bl equals, and then over here, I'll get epsilon ijl d iaj minus dj ai. Okay, but this guy's antisymmetric on I and j, and so are these, so you can just remove one of those and put a factor of 2. So this is twice epsilon, and furthermore, I can shunt this index L around to the front. Remember, epsilon is odd under permutations, so if this moves through 2 indices, the sign doesn't change. If it moves through 1 index, the sign changes. Moves through 2 index, it doesn't change. So epsilon Lij dij. And so this tells me that B is curl A. And likewise, we can show that the electric field is minus the gradient of phi minus dA dt. Okay, so for electrostatics, we only ever use this term. Electric field is minus grad phi, but when you do full electrodynamics, there's another contribution to the electric field, which is the time derivative of the vector potential. So, so what we see is that, again, all these things become much simpler and more unified in this new notation. So a final bit of notation. We can reduce 2 further. So equation 2, so we had the alpha f beta gamma plus d gamma f alpha beta plus d beta f gamma alpha equals 0. This is equivalent to the equation epsilon alpha beta gamma delta times d beta f gamma delta equals 0. Okay, so what is that epsilon? Epsilon is just the 4D analog of the 3D epsilon. So epsilon alpha beta gamma delta is defined to be 1 if, let me define it this way. Defined. So defined by epsilon 0, 1, 2, 3 equals 1. Epsilon alpha beta gamma delta is equal to 1 if alpha beta gamma delta is an even permutation. of 0, 1, 2, 3, minus 1 if it is an odd permutation, and 0 otherwise. So epsilon is the totally antisymmetric tensor in 4 dimensions. To see that this is equivalent to that, you have to use the fact that F is antisymmetric. Okay, so if you simply write out the components of this guy, so it's telling you that if I pick alpha equals 0, right, then I have beta gamma delta must be 1, 2, 3, some permutation of 1, 2, 3. This will give me, for example, D1 F2, 3. Then I will get D2 F1, 3 and D3 F1, 2. And so there are actually 6 different terms, but they pair up because this guy's antisymmetric. And if you write them out, you'll find they're exactly those combinations. So these two equations are completely equivalent. And later in the course, we're going to use this epsilon tensor. So let me just summarize. Okay, we have reduced all of electrodynamics to d alpha f alpha beta equals minus mu naught j beta, and epsilon alpha beta gamma delta d beta f gamma delta equals 0. So that's an amazing feat, given that actually electrodynamics is responsible for almost every phenomenon in nature. The colors of things, the waves which travel, the interaction between molecules and atoms. So that's sort of, in some ways, the majority of natural phenomena relate, or almost all natural phenomena relate to these things, plus the fact that the particles are charged, that there are charged particles in the universe. But these equations really describe the forces between them and the radiation between them. But that's not the, we still have, so far it's just notation. We've made them more compact. What we're going to see next time is that in this new notation, it's obvious that these equations have a symmetry. And the symmetry connects the components of 4 vectors, just like rotations connect the components of a 3 vector. If I'm in space, I have x, y, z. If I do a rotation, x transforms into y and z, and y into x and z, and so on. What we've done is unify space and time, and so rotations in space-time are going to be a symmetry of these equations. And that, of course, is relativity. So are there any questions people have? Yeah?
What was the phi here?
Sorry?
The phi.
Phi is the electrostatic potential. Okay, so phi is the or we sometimes called the electric potential. Okay, it's defined in electrostatics so that E equals minus the gradient of phi. Okay, and A is the magnetic vector potential. And that's defined in magnetostatics so that B equals curl A. Okay, the reason you can define that is, you see, in electrostatics, curl E is 0, because things are static, right? So there's no d by dt's if it's static. So curl E is 0. If curl E is 0, this implies that E can locally be written as the gradient of something. Okay, you can see that's consistent because the curl of a gradient is 0. Okay, it's actually implied because the potential, if curl E is 0, then you can write down this, which is E dot dx. I can pick an arbitrary point and integrate the electric field along an arbitrary curve, okay, to the point x. And this defines phi of x. And obviously, the gradient of phi is just d by dx of this integral. Gives you, the gradient of phi gives you E. Now, the important point is that phi is a single-valued function of x because it doesn't matter what this path is. As you see, if curl E is 0, if I deform the path, the difference between this contour and that contour is the integral of E around this closed loop. And that, by Stokes' theorem, integral of curl E dx is integral of E dot dl is integral of curl E over the area, which is 0. So this is the electrostatic potential. And similarly, in magnetostatics, you see I've got some current, which is sourcing my magnetic field, but I don't have any time dependence. So now curl B is not 0, okay, but div B is 0. So if div B is 0, B can be written as the curl of a vector field, curl A, because div of curl A is 0. And through a similar argument, you can show that A, the vector potential, exists. Okay, so these potentials are very useful in electromagnetism. And likewise, when we do electrodynamics and quantum electrodynamics, this vector potential is extremely useful. Okay, in fact, it emerges here as a sort of mathematical trick. I've got these field strengths. They are fundamental quantities, the electric and magnetic fields, but I can, through this trick, write them as the gradient of something. Okay? It's much more than a trick. It turns out that this vector potential actually, in some way, exists. Okay? And the most dramatic case of that is the Aharonov-Bohm effect, where you have a particle which propagates in a region with 0 magnetic field, but it goes around a magnetic flux. And even though the particle never enters the region of magnetic flux, the integral of A dot dx around the flux, so here's my B field, and I move the particle around, this is not 0. In fact, this is equal to the flux through the loop. And this is observable in quantum mechanics. It gives you a phase which is observable. So this is quite typical in physics. You introduce something for mathematical or symmetry reasons, looks like a rather, just a mathematical construction, and then later on you figure out how to actually measure it. And that's the way that fields were introduced. Electric fields were not thought to be real. Okay, they weren't thought to, they were thought to, it was thought by Newton that forces act at a distance. I have some mass, it attracts another mass. Likewise, Coulomb thought, I have electric charge, it repels or attracts another electric charge at a distance. The field was just a mathematical device to describe that force. Okay, it was really Faraday who said, this doesn't make sense. The field must exist. Okay, because he said, if I've got these two masses pulling on each other, and I move this one suddenly, how does this one know instantaneously? Imagine it's on the other side of the universe. Why should it know instantaneously that I've moved the one that's pulling or pushing it? He said, that's ridiculous. And so he said, it must be that actually there is a field, and it carries the influence of one charge on another. It was Faraday's insight. Faraday tried for 30 years to persuade other scientists in London that fields were real, and none of them believed him. Okay, they all thought he's delusional until Maxwell came along. And then Maxwell's equations really describe the fields, and light is nothing but fields. So if you don't believe in fields, you don't believe in light. And so, so that persuaded people that fields are real. Any other questions? Yeah.
You mentioned forces now, and in your summary of all of electrodynamics, that doesn't tell anything about forces, right?
That's a very good point. So what I have not done is describe how, so forces are things, for example, between particles. If we have some charged particles, how are they affected by the fields? That is the question of how does this current evolve? I need some equation for the current. I've told you it's conserved. D mu J mu is 0, and that's electric. By the way, this equation implies that d beta J beta equals 0. Can you see that? If I take the partial beta derivative here, this guy's symmetric because they commute. It's anti-symmetric. So this equation immediately implies current conservation. But that doesn't tell you what the current does. It's only one equation. And so we need some equation that tells you how the electric charges move. And so that is, I believe, what we are going to do in the yeah, we're going to do that in the next lecture. So it turns out that all of this notation almost forces, well, in fact, it does, in a sense, force particles to react to electric fields in exactly the way we know they do, with the Lorentz force. Okay, once you've set this up and you try to write an equation for a particle, you've got no option but to have the Lorentz force. Okay, we'll see that next time. And furthermore, it turns out the particle couples directly to this guy. Doesn't couple, how should I say? When we write the Lagrangian for the particle, we can't use F. It's not possible to write a Lagrangian for a particle coupling to F. You have to couple it to A. So the particle sees A. Any other questions? Okay, thanks a lot. I think your next lecture is 11, I hope? 10:45? Okay, so you got a bit of a break.